Have you ever followed a recipe to bake a cake? You measure out the flour, you crack the eggs, you follow every step just to get that perfect result. Well, what if I told you that chemists do the exact same thing? It's just that their kitchen is a lab and their ingredients are atoms. So let's crack open this ultimate recipe book and see how chemists cook up, well, everything in our world, one atom at a time. All right, so here's what's on the menu today. First, we're going to see how a reaction is basically just a recipe. Then we'll get into how chemists count their ingredients, which is trickier than it sounds. After that, we'll figure out what happens when you run out of something. Then we'll compare the recipe to what you actually get. And finally, we'll explore the incredible idea of a perfect zero-waste reaction. Okay, so let's dive right in with that big idea. How is a chemical reaction just like baking a cake? It might sound a little simple, but I promise you, this one analogy is the key to understanding this entire process. And it's kind of crazy how well the language translates. In the kitchen, you've got your ingredients. In the lab, you've got reactants. The recipe card with all the instructions, that's just the chemical equation. And the finished cake? Yup, that's your product. It's the exact same logic, right? Following a set of instructions to create something new. But here's the problem. How do you measure ingredients that are so small you can't even see them? I mean, you can't just scoop up a cup of hydrogen atoms. So to solve this, chemists came up with this sort of universal currency for counting atoms, and it's called the mole. Yeah, the mole. And just think about it like this. A dozen always means 12, no matter what you're talking about, right? A dozen eggs, a dozen donuts, it's always 12. Well, a mole is the exact same idea for chemists. It's a standard unit that gets everyone everywhere on the same page. It's how they measure their atomic ingredients with perfect consistency. And this is the number. It's called Avogadro's number, and it is just mind-boggling. We're talking over 600 billion trillion. That's how many atoms you'll find packed into a single mole. The scale is almost impossible to wrap your head around, but believe it or not, this gigantic number is the key that makes all the math and chemistry actually work. Okay, let's head back to our kitchen. Imagine your recipe calls for 3 eggs, but you open the fridge and you've only got 2. What happens? Well, you can't make the full cake, simple as that. The number of eggs limits your production. Well, guess what? The exact same thing happens in chemistry. In chemistry, this is called the limiting reactant. It's the ingredient that gets completely used up first, and once it's gone, the whole reaction just stops. So, in short, the limiting reactant is the boss. It's in control. It determines the absolute maximum amount of product you can possibly hope to make. So how do chemists find that one crucial ingredient? It's actually a pretty straightforward 3-step playbook. First, they balance the equation to get the ratios right. Second, they convert the amounts of each reactant they have into moles, our universal currency. And finally, they just check those ratios to see which reactant is going to run out first. And boom, that's your limiting reactant. Okay, let's put this into practice with a super classic example, making water from hydrogen and oxygen. The recipe here says we need 2 parts hydrogen for every 1 part oxygen. Now, let's say we start with 2 moles of each. Which one do you think is going to run out first? All right, let's look at the math. The equation tells us that 2-to-1 ratio is key. So if we look at the table, our 2 moles of hydrogen can produce a maximum of 2 moles of water. That's its ceiling. But our 2 moles of oxygen, they actually have the potential to make 4 moles of water. So since hydrogen maxes out at a lower amount, it's our limiting reactant. The reaction will stop dead once 2 moles of water are made, and we'll even have some oxygen left over. Now, every baker knows that just because a recipe says it makes 2 dozen cookies, you don't always end up with exactly 24, right? Maybe some dough stuck to the bowl, or 1 got burned. Well, the lab is no different. There's the recipe, and then there's reality. And this brings up 2 really important terms. First, there's the theoretical yield. That's the perfect on-paper amount you calculate. Then you have the actual yield, what you really end up with in the flask. You know, thanks to spills, unexpected side reactions, or just plain human error. The actual yield is almost always a bit less than what the theory says. To measure how successful a reaction was, chemists use percent yield. It's a simple but really powerful formula. You just divide the amount you actually made by the amount you were supposed to make, and then multiply by 100. It's basically like a report card for your chemical reaction. So take this real-world example from copper production. On paper, the calculation promised 72.4 grams of copper, but in the lab, they only collected 58.3 grams. When you run the numbers, that works out to a percent yield of 80.5%. which isn't bad at all, but it's a really clear example of that gap between the recipe and reality. But what if we could get closer to a perfect reaction? What if we could design a process that wasn't just efficient in its yield, but also in its use of every single atom? This is the core idea behind a whole field called green chemistry. The key metric here is called atom economy, and it asks a really simple question. Of all the atoms you put into a reaction, what percentage of them ended up in the useful product? The higher the number, the less waste you're creating in the form of unwanted byproducts. In this nickel production process, for example, the atom economy is about 68%. That means nearly a third of all the starting material isn't turned into valuable nickel, but into carbon monoxide, a wasteful and toxic byproduct. Improving that atom economy would mean creating less pollution and more product from the very same ingredients. And this brings us to a powerful final idea. When we master these chemical recipes, maximizing yield and pushing atom economy towards 100%, we're not just doing better chemistry. We're designing cleaner, smarter, more sustainable industries from the atomic level up. So the real question is, how will zero-waste chemistry change our world?